Hey everyone, I hope you all are doing absolutely fine. My name is Pranav Durai. I am a computer vision engineer at Big Vision LLC, San Diego, USA. And I'm also a research fellow at Stanford University School of Medicine. I'm working along with Dr. Fresky on a very interesting project. So that's pretty good. So if you've used computer vision before, I'm pretty sure that you would know about OpenCV. And I'm also an active member of the Computer Vision Foundation. And today, my presentation will be focused on fast generalized object segmentation on medical imagery using SAM algorithm. So let's get in. So segmentation, a small introduction before we start. Image segmentation is actually the process of dividing an image into distinct and meaningful regions based on certain characteristics such as color, intensity, texture, or object boundaries. So over here on the screen, we can see the classical approaches that people have been following for segmentation for all of these years. So you have color-based thresholding over here on the left. You have region of interest-based thresholding on over here. I mean, this is pretty similar to what Dr. Horatio showed in his previous lecture, and this is good as well. And also, we also have intensity-based thresholding, thresholding based on some particular or specific parameters. But then, what is the problem over here? What is the problem with these approaches? The first thing is that because of the multimodal structure of medical imaging, it is sensitive to noise, right? So when we try to image stuff, there's a lot of noise and artifacts that get in the image data. So we do have our RGB image over here. And again, you might have noise factors within the image. And varying intensity levels, right? If you're trying to threshold a particular image, the threshold value for each image will vary, right? You can't have a preset value and try to segment objects or structures out of it. The third one is complex tissue structures, right? We may have tissues which may overlap, right? So how would you segment that? You can also have tissues with different areas, right? So how would you effectively segment that? Multimodality imaging, again, this also brings in a lot of complexity into traditional thresholding problems. This feature on optimal thresholding selection also depends on varying intensity levels. And also, because of this, we may have incomplete object segmentation. So the question is, can AI accelerate segmentation tasks, right? So it turns out it can. So let's look into a deep learning based approach, a small pipeline that might assist with this kind of a problem. So you can see that you can use a tool like CVAT to annotate 2D slices of some structure, right? So over here we have a brain MRI data set, and the ground truth masks over here have been done using the CVAT tool. And this is manually done by some annotator who already has medical knowledge of what these structures are. Now you pass this to a segmentation model, right? You build this model using AI frameworks like TensorFlow and PyTorch, and you train these models with millions of images of your particular data set with masks, right? Which ground truth masks on top of it. And there are a lot of segmentation models which are available currently. So you have UNet, UNet++, you have mask RCNN, which is shown over here, HRNet, SegNet, PSPNet, and SAM. And SAM is the one which we'll talk about in this particular presentation. But after you train your model, this is the inference, right? This is the prediction from the model itself. And let's look at a small comprehensive comparison over here. So this is the ground truth. This is the mask, which was annotated by a human. And this is the prediction, which was given back by the segmentation model. And you could really see that, even if you try to overlap these masks, it would be like 99% accurate. And this is crazy, right? So it takes very less time if you're running on really, compute-intensive systems, right? So this is where SAM comes in. So this is SAM, and it's called Segment Anything Model. And it is actually from this company called Meta. You might know Meta as Facebook, right? So basically the architecture looks like this. You have an input image, it passes through the image encoder over here, and image embeddings are generated for each image that you put into this model. You also give it a mask, right? The ground truth mask. that is passed into the convolutional layer. And you also have a masked decoder, right? And you can pass in few parameters as prompts, right? So it can be points in the image where the specific mask is present, or it can be a bounding box, or it can also be a textual prompt where you can say that, hey, there is this structure in this particular region of the image. And based on this, the model will be able to generate valid masks, right? So this is a autonomous car. There's a camera which is placed on top of the autonomous car, and it moves. And we can see that in real time, we can see all of the segments, and all of these segments are color matched over here on the right. So SAM was, trained on 1 billion masks on 11 million images, right? So this is something. But again, if you fine tune SAM, we can use it for medical purposes, all right? Fine tuning is the process of, making a specific AI model more specific for your specific use case, for your particular use case, right? So in this case, you're trying to perform inference on medical images. So you fine tune the already pre-trained model with custom data from your experiments, right? So so these are a few images, right? You can see the ground truth over here. This is the mask which was annotated by a human who knows what this stuff is. You can also see an example over here. And this is a prediction by normal SAM, which was not fine-tuned on medical data. Over here, you can see that the edges of the masks is not really that great. There is another model called UNet, which we saw previously. And that was okay. But again, there are some jagged edges over here, right? And finally, you do have MedSAM, which has a very smooth segmentation mask around this particular place. When you're trying to evaluate the performance of segmentation models, you need to consider this metric called a DSC. That's called a dice similarity coefficient. You basically overlap the ground truth with the prediction mask and try to see how much of it overlaps, right? So if you have a 99% or 100% overlap, then that is a robust model. So over here, we're able to achieve somewhere around 98.61, which is great. So, all right. So this was my presentation. If you'd like to connect with me, you can Google my name. And thank you very much for the opportunity. This was a very great learning experience. And coming from an engineering background, trying to learn medical stuff was pretty impressive and exciting. So yeah, thank you very much. Thank you for the opportunity.